This is TWiT.
So as I said at the top of the show, I was originally going to title this week's podcast Newly Vulnerable, since we talked about a bunch of new vulnerabilities, and then put them all at the end. And I was going to place the Lamphone under This Week in Wacky Surveillance Technology category. But as they always do, the researchers have a quite serious 15-page research paper, which, you know, always hooks me. And their work will be presented at Black Hat in August, the virtual Black Hat conference. So I decided that it won the top spot for this week's title and topic. And no one will be surprised to learn that this research hails from the Ben Gurion University of the Negev and the Weizmann Institute of Science, which produces a steady stream of new and imaginative data exfiltration schemes. Remember the singing capacitors of our power supplies? That was from those guys, too. And what makes their work stand out is that they always wrestle every wacko scheme to the ground, applying solid science and physics to the challenge. In the show notes, I have a schematic of their attack, which in the left-hand frame shows a couple of people talking, and that creating, you know, sound vibrations in the air, which apparently causes some micro vibrations in the surface of a light bulb, like, you know, hanging from the just regular light bulb hanging from the ceiling. Then in their experiment, up to, I think it was 27 yards, maybe it was more than that. We'll get to it in a second. I mean, at some good distance away, they were able to use a telescope looking at the light bulb and a photodiode-based sensor to detect the micro vibrations that the light bulb was subjected to just from regular conversation in the room. Now, the light bulb, of course, is far from being a high-quality microphone. It's anything but they were able to work out the details. So this time I'm going to skip the abstract of their paper, which I normally share. Instead, I'm going to share their introduction, since this really does, it turns out, represent an advance in the state-of-the-art of eavesdropping attacks, thanks to the back-end computational transform that's needed to convert a light bulb's highly nonlinear frequency response into reconstructed speech. You know, if you think about a tuning fork, you know, as we all know, you thwack it and it vibrates at its natural resonance frequency. So, you know, in terms of speech, it's an extremely sharp bandpass, a very narrow bandpass filter, and a light bulb is not much better. So, you know, think about like a wine glass. You can ting the side, right? And it'll, if it's crystal, it'll vibrate again at its natural resonance frequency. So rather than directly obtaining the speech waveform, what you get is more of a speech frequency modulated amplitude modulation. So they had to do some work in order to extract speech. So anyway, they explained this. They said, introduction. Eavesdropping, the act of secretly or stealthily listening to a target or victim without his or her consent by analyzing the side effects of sound waves on nearby objects. For example, a bag of chips. Remember, we talked about that years ago. You were, you know, looking at the vibration of a bag of chips and were able to extract the speech from it. And devices, motion sensors, for example, is considered a great threat to privacy. Is that in the past 5 years, various studies have demonstrated novel side channel attacks that can be applied to eavesdrop via compromised devices planted in physical proximity of a target or victim. In these studies, data from devices that are not intended to serve as microphones, for example, motion sensors, speakers, vibration devices, and magnetic hard drives are used by attackers to recover sound. Sound eavesdropping, based on the methods suggested in the above-mentioned studies, is very hard to detect because applications and programs that implement such methods do not require any risky permissions, such as obtaining data from a video camera or a microphone. As a result, such applications do not raise any suspicion from the user or operating system regarding their real use, eavesdropping. However, such methods require the eavesdropper to compromise a device located in proximity to the target victim in order to obtain data that can be used to recover sound and exfiltrate the raw processed data. They said to prevent eavesdroppers from implementing any of the above-mentioned methods which rely on compromised devices, organizations deploy various mechanisms to secure their networks. For example, air-gapping the networks, prohibiting the use of vulnerable devices in sensitive areas, using firewalls and intrusion detection systems to prevent exfiltration. As a result, eavesdroppers typically utilize three well-known methods that don't rely on a compromised device. The first method exploits radio signals sent from a victim's room to recover sound. This is done using a network interface card that captures Wi-Fi packets sent from a Wi-Fi router placed in physical proximity of a target or victim. While routers exist in most organizations today, the primary disadvantages of these methods is that they cannot be used to recover speech, or they rely on a previously collected dictionary to achieve their goal. In other words, it only works from previously known words. And we talked about this sort of something related a long time ago, how reflected Wi-Fi signals could be used to detect a person's emotion or movements within a room. And apparently, a group of researchers managed to detect the much smaller movements of the mouths of people speaking via Wi-Fi signals and then mapped them back into what they must be saying. Needless to say, it was strictly a proof of concept and would hardly be practical. Anyway, our guys continue saying, the second method, a laser microphone, relies on a laser transceiver that is used to direct a laser beam into the victim's room through a window. The beam is reflected off of an object, or maybe the window itself, and returned to the laser transceiver, which converts the audio modulated returning beam into an audio signal. In contrast to the previous limited radio-based methods, laser microphones can be used in real time to recover speech. However, the laser beam can be detected using a dedicated optical sensor. The third method, the visual microphone, exploits vibrations caused by sound from various materials, a bag of chips, a glass of water. I think we talked about balloons once. You could have like inflated balloons in a room, and the balloon would vibrate, it being relatively elastic and pretty easy to pick up sounds. They said in order to recover speech by using a video camera that supports a very high frame rate per second, high FPS, of over 2200 hertz. In contrast to the laser microphone, the visual microphone is passive, so its implementation is much more difficult for organizations and victims to detect. However, the main disadvantage of this method, according to the authors, is that the visual microphone cannot be applied in real time because it takes a few hours to recover a few seconds of speech, since processing the high resolution and high frequency 2200 frames per second video requires significant computational resources. In addition, the hardware required, a very high frame per second video camera, is expensive. So, They said, in this paper, we introduce Lamphone, a novel side channel attack that can be applied by eavesdroppers to recover sound from a room that contains an exposed hanging light bulb. Lamphone recovers sound optically via an electro-optical sensor, which is directed at a hanging bulb. Such bulbs vibrate due to air pressure fluctuations, which occur naturally when sound waves hit the hanging bulb's surface. We explain how a bulb's response to sound, a millidegree vibration, actually I think it ended up being microdegree vibration, can be exploited to recover sound. And we establish a criterion for the sensitivity specifications required of a system capable of recovering sound from such small vibrations. And I was actually thinking I should have called this, good vibrations or bad vibrations or something. But anyway, speaking of which, Leo, did you ever see this is completely off topic, but I sent a note out to my friends. Did you ever see Yesterday when I was in the theaters? The movie?
Oh yeah, I loved it
because
too.
Okay, because it's available on Netflix, and Laura and I rewatched it.
The Beatles never existed.
Friday.
Yeah. And Dev has a bike accident and somehow enters a different dimension where the Beatles never existed, but he remembers all the Beatles songs, so he becomes a massively successful songwriter.
Yeah. Very cool. So for what it's worth, completely just
what does that have to do with this?
Nothing, not at all. Except I was talking about good vibrations.
Of course, that's the Beach Boys.
That's the Beach Boys.
I get your
not the Beatles, but
logic. I can.
Yes.
Yeah, you enjoyed it. Yeah, it's a good movie. I really liked it.
I really did.
Made me feel
and speaking of which, since I'm off topic, it turns out, remember Devs, the show that we loved?
Yeah.
The 8-episode series on Amazon.
Yeah.
The co-producer is a Security Now podcast listener. The reason Devs was as accurate as it was is because of this podcast.
No. Because remember, I recommended it to you because in the first 15 minutes, there's a debate over elliptic curve cryptography versus RSA. And I thought, gee, that's pretty good.
From the podcast.
Son
and in fact, when some of the actors wanted some help in getting a sense for what techie talk sounds like, he said, listen to a couple episodes of Security Now.
Oh, man.
So
when they bring that back, I don't know if they can. I guess they're kind of done, but
the loop is complete.
Wow,
it was really fabulous. If anyone, it was on Amazon Prime, and absolutely top recommendations. So
that's such a fun
anyway. I thought
story.
that was very cool.
That's wonderful. Yeah, nice.
Anyway, so they say, then we evaluate so they determine the criterion for the sensitivity specifications of a system capable of recovering sound from such small vibrations. They said, then we evaluate a bulb's response to sound, identify factors that influence the recovered signal. Like I said, these guys go all the way, and characterize the recovered signal's behavior. We then present an algorithm we developed in order to isolate the audio signal from an optical signal obtained by directing an electro-optical sensor at a hanging bulb. We evaluate Lamphone's performance on the tasks of recovering speech and songs in a realistic setup. We show that Lamphone can be used by eavesdroppers to recover human speech, which can be accurately identified by Google Cloud Speech API. And I added, which I suppose means that it would be possible to set up an entirely automated listening station which triggers human involvement only when specific keywords were voiced, because Google's Cloud Speech API could be, doing speech recognition on the fly, turning it into text, looking for keywords, and then letting someone know.
Unbelievable.
And they also said singing, which can be accurately identified by Shazam and SoundHound. Oh, yeah. From a bridge located 25 meters, 27 yards away from the target office containing the hanging light bulb.
Wow.
They said, we discuss potential improvements that can be made to Lamphone to optimize the results and extend Lamphone's effective sound recovery range. Finally, we discuss countermeasures that can be employed by organizations to make it more difficult for eavesdroppers to successfully use this attack vector. So I was unsure how much time we would have, but we do have a little bit more. So I'll share a little bit just so our listeners can get a sense for what they did. In section 4 of the paper, bulbs as microphones, they said, we measure the vibration of a hanging bulb and we establish a criterion for the sensitivity specifications for a system capable of recovering sound from these vibrations. Experimental setup. We attach a gyroscope, the MPU-6050GY-205216, for anyone who wants to duplicate, to the bottom of a hanging E27 LED light bulb, parens 12 watts. That bulb was not illuminated during this experiment. A Raspberry Pi 3 was used to sample the gyroscope at 800 hertz. We placed Logitech Z533 speakers very close to the hanging bulb, 1 centimeter away, and played various sine waves at 100, 150, 200, 250, 300, 350, and 400 hertz from the speakers at 3 volume levels, 70, 95, and 115 dB. We obtained measurements from the gyroscope while the sine waves were played. Results. Based on the measurements obtained from the gyroscope, we calculated the average peak-to-peak difference in degrees for theta and phi. The average peak-to-peak difference was computed by calculating the peak-to-peak difference between every 800 consecutive measurements that were collected from 1 second of sampling and averaging the results. The frequency response was a function of the average peak-to-peak difference, revealing 3 interesting insights. The average peak-to-peak difference for the angle of the bulb is 1, very small, 0.005 to, okay, so it is milli, to 0.06 degrees.
Wow.
So that's between 5 and 60 millidegrees. Wow. 2, increases as the volume increases, okay, not surprisingly. And 3, changes as a function of frequency, which you would expect, right? Because it is far from being a neutral frequency response. You know, you don't buy your light bulbs based on, has a flat frequency response within 3 dB. No.
I might start.
Based on the known formula of the spherical coordinate system, we calculated the 3D vector, they say XYZ, that represents the peak-to-peak vibration on each of the 3 axes by taking the distance between the ceiling and the bottom of the hanging bulb into account. We calculated the Euclidean distance between this vector and the vector of the initial position. The results show that sound affected the hanging bulb, causing it to vibrate in 300 to 950 microns between the range of 100 and 400 hertz. Then under capturing the optical changes, we now explain how attackers can determine sensitivity of the equipment, an electro-optical sensor, a telescope, and an A to D converter, needed to recover sound based on a bulb's vibration. We've established the criterion for recovering sound. The attacker's system, consisting of an electro-optical sensor, a telescope, and an analog-to-digital converter, must be sensitive enough to capture the small optical differences that are the result of a hanging bulb that moves in 300 to 950 microns. In order to demonstrate how eavesdroppers can determine the sensitivity of the equipment they will need to satisfy the above criterion, we conduct another experiment. Experimental setup. We directed a telescope at a hanging 12-watt E27 LED bulb. And I have, as I said, I have a diagram at the top of the show notes. We mounted an electro-optical sensor, the Thorlabs PDA 100A2, which is an amplified switchable gain light sensor that consists of a photodiode, which you need for frequency response. A phototransistor is not fast enough, says he who did the light pen for the Apple II, used to convert light to electrical voltage to the telescope. The voltage was obtained from the electro-optical sensor using a 16-bit A to D converter, the NI9223 card, and was processed in LabVIEW script that they wrote, or that we wrote, they said. The internal gain of the electro-optical sensor was set at 50 dB. We placed the telescope at various distances, 100, 200, 300, 420, 670, 830, and 950 centimeters from the hanging bulb and measured the voltage that was obtained from the electro-optical sensor at each distance. The results of this experiment were used to compute the linear equation between each two consecutive points. Based on the linear equations, we calculated the expected voltage at 300 microns and 950 microns of bulb displacement. From this data, we can determine which frequencies can be recovered from the obtained optical measurements. A 16-bit A to D with an input range of from -10 to positive 10 volts. For example, the NI9223 card used in our experiments provides a sensitivity of 300 microvolts provided by our 16-bit A to D converter, which is sufficient for recovering the entire spectrum from 100 to 400 hertz in the 200 to 300 centimeter distance range. Because the smallest vibration of the bulb, 300 microns from this range, is expected to yield a difference of 300 microvolts. However, this setup cannot be used to recover the entire spectrum in the 670 to 830 centimeter range, so an A to D converter that provides a higher sensitivity is required. And anyway, they go on like that, and you get the sense. It is now possible. They ended up verifying after they'd calibrated everything and figured out what equipment they needed. They did do the 27-yard experiment with a light bulb and people talking in the room. It is now the case that anybody talking in a room which is visible to the outside can be overheard if there's something in the room that is vibrating, because we now have the technology to look at it and recover the speech in the room from that. So congrats to the guys at the Ben Gurion University and the Weizmann Institute of Science. And I wonder who else might be reading their paper with interest.
Come on, Steve. The NSA's had this for years. You know they have.
That's true. That's true. This is not news for them.
I mean, you could even speculate this would be possible. So I'm sure they thought of this way back when. It's cool, though. It's cool research and not surprising at all. Yeah. I'm sure plate glass windows vibrate. It's just a question of whether you can measure such a small vibration, And
well, in fact, we know that a laser interferometer will do that.
Sure.
So you can bounce a laser, but then you're going to see a red spot on the window.
Right.
And so what's cool about this is that they wanted to take a totally passive approach. Nothing in the room, no listening devices, just find something that's vibrating. And my goodness, think about it.
Everything vibrates.
Yes, exactly.
Right.
So, I mean, and a light bulb is relatively rigid. So it's going to be, it's going to be resistant to vibration compared to like a leaf on a plant, a plant in a flower pot or something.
Yeah.
So they tackled the tough one.